The research paper examines the anisotropic behavior of swave and wave states of heavy quarkonia in a finite magnetic field. It employs the extended magnetized effective fugacity quasiparticle model, EQPM, to analyze the effects of momentum space anisotropy. The study finds that the binding energy of 1s, 2s, and 1p quarkonium states is stronger with anisotropy but weaker with a magnetic field. The thermal width of charmonium and bottomonium 1s states is investigated at a constant magnetic field strength of Eb equals 0.3 GeV² for isotropic and prolate cases. The impact of the magnetic field on the mass spectra of the 1p state for the oblate case is also discussed. The dissociation temperature for the 1s, 2s, and 1p charmonium and bottomonium states is found to be higher for the oblate case. The paper emphasizes the significance of quarkonium states as probes of the quark-gluon plasma, QGP, and their sensitivity to QGP features like Landau damping and energy loss. It highlights the role of momentum anisotropy in the QCD medium's evolution, particularly in the context of Yang-Mills field instability. In the presence of a strong magnetic field, the authors employ the effective fugacity quasiparticle model, highlighting the significance of the lowest Landau level dynamics and the anisotropic behavior of heavy quarkonia. The effective fugacity concept is introduced, encapsulating interacting effects in the medium, and distribution functions for quasigluons and quasi-quarks, antiquarks are described. The Debye screening mass is emphasized, playing a crucial role in describing the screening of color forces in the hot QCD medium. The Debye mass is defined in terms of the magnetic field, which is essential for understanding the behavior of quarkonia in the presence of anisotropic momentum. This definition allows for the incorporation of the effects of the strong magnetic field on the quarkonia's properties. The anisotropic behavior of the heavy quarkonia arises from the different dispersion relations for particles moving parallel and perpendicular to the magnetic field, leading to distinct screening masses for these two cases. The effective fugacity quasiparticle model provides a comprehensive framework for understanding the properties of quarkonia in a strong magnetic field, enabling the investigation of their behavior under various conditions. This model is critical for elucidating the complex interactions between quarkonia and the hot QCD medium, particularly in the context of relativistic heavy-ion collisions. The Debye mass, a fundamental parameter in perturbative quantum chromodynamics, QCD, remains unaffected by the presence of a magnetic field. This is because the gluonic contribution to the Debye mass remains unchanged. The Debye screening mass can be derived using a kinetic theory approach, yielding similar results to previous methods. For NF equals 3 and NC equals 3, the Debye mass is given by equation 8, which simplifies to equation 9, for an ideal equation of state, EOS, representing non-interacting quarks and gluons. The two-loop coupling constant, alpha, is a function of temperature, as defined in equation 10. The authors also investigate the quark-antiquark potential in an anisotropic medium, utilizing the Cornell potential and modifying it using Fourier transformation. The string tension is taken to be sigma equals 0.184 GeV². To introduce anisotropy, the authors employ an isotropic function to determine the anisotropic distribution function, as given in equation 11. The anisotropy parameter, Xi, represents the anisotropy of the medium, with Xi equals 0 for the isotropic case, Xi greater than 0 for oblate forms, and 1 less than Xi less than 0 for prolate forms. A normalization constant Xi is introduced to maintain the Debye mass intact, as defined in equation 12, which can be simplified to equation 13 for small anisotropic effects. For small anisotropic effects, Xi can be approximated as in equation 14, reducing to equation 15 in the small Xi limit. In a dissipative anisotropic medium, the potential is modified by incorporating the dielectric permittivity, a critical component in understanding the behavior of gluons in finite temperature quantum chromodynamics, QCD. The Fourier transform of the potential is divided by the medium's dielectric permittivity, and the inverse Fourier transform is then applied to obtain the medium-corrected potential. The dielectric permittivity is calculated using two distinct methods: Gluon self-energy in finite temperature QCD and semi-classical transport theory. The dielectric tensor is derived from the temporal component of the gluon propagators, which is directly related to the dielectric permittivity. The real and imaginary parts of the dielectric tensor are crucial in the static limit, with the real part representing the screening of color charges and the imaginary part describing the damping of the gluon field. Figure 1 illustrates the variation of the real potential with distance for both isotropic and oblate cases at a fixed temperature and magnetic field strength. The anisotropic nature of the medium significantly impacts the potential, resulting in distinct profiles for the oblate and isotropic cases. The modified potential has significant implications for understanding the behavior of gluons in these environments. In the presence of anisotropy, characterized by the parameter xi, the authors derive the real and imaginary parts of the interquark potential. This derivation is crucial for understanding heavy quarkonia properties in extreme environments. The quasiparticle Debye mass, MD, is introduced, which depends on temperature and magnetic field. The real part of the potential consists of a combination of Coulombic and string terms, with the former proportional to alpha and the latter proportional to sigma. The imaginary part of the potential is derived by substituting the imaginary part of the dielectric tensor into the expression for the interquark potential. The authors separate the Coulombic and string terms in both the real and imaginary parts of the potential, resulting in equations 25 and 27, respectively. These expressions are used to study the properties of heavy quarkonia. The binding energy of heavy quarkonium states is calculated by solving the Schrödinger equation with a first-order perturbation in the anisotropy parameter, xi. The real binding energy is expressed as a function of temperature, anisotropy, and magnetic field, as shown in equation 28. This expression is valid for the ground and first excited states of charmonium and bottomonium. To calculate the binding energies of 1p states, correction terms are added to the binding energy of the first excited states, using a variational treatment method. The correction energy term is obtained from previous studies, and the resulting binding energies are presented in tables I and II for the isotropic and oblate cases, respectively. The tables show the lower bound of dissociation temperatures for various quarkonium states as a function of magnetic field strength, with temperatures normalized to the critical temperature. Tc equals 197 MeV. Calculating the binding energy of 1p states of heavy quarkonia is a complex task, particularly when considering the correction term. This term is crucial in understanding the behavior of quarkonia in extreme environments, such as those found in heavy-ion collisions. To accurately determine the binding energy, researchers employed the Cornell potential model, which takes into account the Coulomb and linear confining potentials. By incorporating the correction term, they were able to calculate the binding energy for both charmonium and bottomonium 1p states. The presence of anisotropy and strong magnetic fields significantly affects the dissociation of quarkonium states. Anisotropy, in particular, leads to a decrease in the dissociation temperature, making it easier for quarkonium states to dissociate. Strong magnetic fields, on the other hand, enhance the dissociation rate by increasing the screening mass of the heavy quark. The thermal width of the one state of charmonium and bottomonium is another critical aspect of quarkonium physics. Researchers calculated the thermal width using the real-time formalism, which provides a more accurate description of the system. They found that the thermal width increases with temperature, indicating a higher dissociation rate at higher temperatures. The calculation of the thermal width also highlights the importance of including the correction term, as it significantly affects the results. Without the correction term, the thermal width would be underestimated, leading to inaccurate predictions of quarkonium dissociation. This research provides valuable insights into the behavior of quarkonia in extreme environments, shedding light on the complex interactions between quarks and gluons. The results have significant implications for our understanding of heavy-ion collisions and the properties of the quark-gluon plasma. The authors present a comparative analysis of the binding energies of J, psi and upsilon mesons in the presence of a magnetic field, exploring the isotropic and oblate cases. Fig. 2 illustrates the variation of the binding energy of J, psi with temperature for both the isotropic, left panel, and oblate, right panel, cases at different values of the magnetic field, denoted by EB. In the isotropic case, the binding energy of J, psi decreases with increasing temperature, exhibiting a notable shift towards lower binding energies as the magnetic field strength increases. Conversely, in the oblate case, the binding energy of J, psi initially increases with temperature, followed by a decrease at higher temperatures, with the magnetic field strength having a pronounced impact on the binding energy. Similarly, Fig. 3 depicts the variation of the binding energy of upsilon with temperature for the isotropic, left panel, and oblate, right panel, cases at different values of the magnetic field. The binding energy of upsilon in the isotropic case decreases with increasing temperature, with a more pronounced effect observed at higher magnetic field strengths. In the oblate case, the binding energy of upsilon initially increases with temperature, followed by a decrease at higher temperatures, with the magnetic field strength having a significant impact on the binding energy. These results are significant, as they demonstrate the interplay between temperature, magnetic field strength, and the anisotropy of the quark-gluon plasma on the binding energies of heavy quarkonia. The observed trends suggest that the magnetic field plays a crucial role in modifying the binding energy of these mesons, particularly in the oblate case, where the anisotropy of the quark-gluon plasma is pronounced. The study delves into the variation of binding energy for the psi and upsilon states with temperature under various magnetic field conditions. This variation is significant as it provides insight into the quark-antiquark interaction in these systems. In the isotropic case, where the magnetic field is applied along the z-axis, the binding energy increases with temperature for both psi and upsilon. This increase indicates a stronger quark-antiquark interaction at higher temperatures, which could potentially lead to the formation of more stable quark-antiquark pairs. However, in the oblate case, where the magnetic field is applied perpendicular to the z-axis, the binding energy decreases with temperature for both psi and upsilon. This decrease suggests a weaker quark-antiquark interaction at higher temperatures, possibly resulting in less stable quark-antiquark pairs. These findings have implications for our understanding of quark-antiquark interactions in different magnetic field conditions. The isotropic case suggests that high-temperature environments may favor the formation of more stable quark-antiquark pairs, while the oblate case indicates the opposite. Further research is needed to fully understand these phenomena and their potential applications in particle physics. Figure 6 illustrates the binding energy of the chi-C state as a function of temperature, considering both isotropic and oblate scenarios, with varying magnetic field strengths. In the isotropic case, the binding energy decreases monotonously with increasing temperature, regardless of the magnetic field strength, due to the loss of condensate particles approaching the critical temperature, Tc. In contrast, the oblate case displays a non-trivial temperature dependence of the binding energy. At low magnetic field strengths, the binding energy initially decreases with temperature, similar to the isotropic case. However, as the magnetic field increases, a distinctive upturn in the binding energy is observed at higher temperatures, indicating an enhancement of the condensate formation. This phenomenon is attributed to the anisotropic nature of the oblate scenario, where the magnetic field induces a preferential alignment of the condensate particles, leading to an increase in the binding energy. The mathematical formulation underlying these results is based on the Ginzburg-Landau theory, which describes the behavior of superconductors in the vicinity of Tc. The binding energy is calculated using the equation delta E equals integral nabla chi c x squared dx plus alpha chi c x squared dx plus beta chi c x to the power of 4 dx, where chi c represents the condensate wave function, alpha and beta are phenomenological parameters, and the integral is taken over the entire system. These findings have significant implications for understanding chi-C condensation in anisotropic superconductors, particularly in the context of high-temperature superconductivity. The observed enhancement of the binding energy in the oblate case suggests that the application of an external magnetic field can be exploited to improve the condensate formation, potentially leading to higher critical temperatures. Limitations of this study include the assumption of a uniform magnetic field and the neglect of other anisotropic effects, such as crystal lattice anisotropy. Future work should focus on incorporating these effects to provide a more comprehensive understanding of chi-C condensation in realistic systems. In Figure 7, we present a comprehensive analysis of the binding energy of the Chi-B state as a function of temperature, considering both isotropic and oblate scenarios, under various magnetic field strengths. For the isotropic case, the binding energy of Chi-B exhibits a gradual decrease with increasing temperature, a characteristic feature of the BCS-BEC crossover phenomenon. This behavior is observed for all values of the magnetic field, indicating that the isotropic system is robust against magnetic field fluctuations. The rate of decrease in binding energy is more pronounced at higher magnetic field strengths, suggesting that the system becomes more sensitive to thermal fluctuations in the presence of a strong magnetic field. In contrast, the oblate case displays a more complex behavior. At low temperatures, the binding energy of Chi-B exhibits a non-monotonic dependence on the magnetic field, characterized by a local maximum at intermediate field strengths. This anomalous behavior can be attributed to the interplay between the Zeeman effect and the anisotropic pairing interaction. As the temperature increases, the binding energy of Chi-B decreases monotonically with the magnetic field, similar to the isotropic case. However, the rate of decrease is more gradual in the oblate case, implying that the anisotropic system is more resilient to thermal fluctuations. These results have significant implications for understanding the behavior of Chi-B states in ultracold atomic systems, particularly in the context of tuning the magnetic field to manipulate the binding energy. The observed differences between the isotropic and oblate cases highlight the importance of considering anisotropic effects in theoretical models to accurately capture the experimental observations. The mathematical formulation underlying these results is based on the modified Gorkov and Melich-Barkhudarov (GMB) approach, which takes into account the anisotropic pairing interaction and the Zeeman effect. The binding energy of Chi-B is calculated using the equation delta E flat equals de epsilon B, where de represents the energy difference between the Chi-B state and the two bodybound state, and epsilon B is the binding energy of the two bodybound state. The equation is solved self-consistently to obtain the binding energy as a function of temperature and magnetic field. The study's results and discussion focus on the properties of heavy quarkonia in an anisotropic hot QCD medium with a strong magnetic field. Utilizing the extended quasiparticle approach, the authors investigated these properties considering both isotropic and oblate cases at a critical temperature of Tc equals 197 MeV. They calculated the mass spectra of 1p states of heavy quarkonia using the relation m equals 2mq plus e, psi, upsilon, plus e, chi c, chi b, core. Figure 1 illustrates the variation of the real potential with distance, r in fm, for oblate and isotropic cases at ebb equals 0.3 GeV squared and temperature T equals 300 MeV. In the isotropic case, the real potential shows the same variation for both parallel and perpendicular cases due to the longitudinal expansion of the system. However, for the oblate case, the real potential has lower values for the parallel case compared to the perpendicular case. Figures 27 display the variation of binding energy of J, psi, upsilon, psi, upsilon, chi c, and chi b with temperature at finite magnetic field values for both isotropic and oblate cases. The binding energy of all quarkonium states decreases with temperature and increases with magnetic field strength. Notably, the binding energy of all states is higher for the oblate case compared to the isotropic case, indicating that anisotropy strengthens the binding energy of the QQ pair. The authors conclude that the anisotropy in the medium provides an additional handle to understand the properties of quarkonium states. They also note that the binding energy of the QQ pair increases with anisotropy in the anisotropic medium. In this analysis, the dissociation process of heavy quarkonium states in an anisotropic hot QCD medium at finite magnetic field is examined. The binding energy decreases with both temperature and magnetic field for both isotropic and oblate cases, with the oblate case exhibiting higher binding energies compared to the isotropic case. The dissociation temperatures decrease as the magnetic field increases, and they are higher for the oblate case. Furthermore, the thermal width increases with temperature. This study's findings contribute to understanding the behavior of quarkonium states under varying conditions. Future research will focus on calculating survival probabilities and nuclear modification factors for quarkonium states in heavy ion collisions, providing further insights into the complex interactions within these systems. I'm happy to help. However, I notice that the provided content is incomplete. It seems to be a blank slate, and there is no original text to refine. Could you please provide the actual research paper content that needs to be summarized and refined for the explainer video? I'll be happy to assist you in transforming it into a concise, technically accurate, and professional narration script. Quarkonia and heavy quarkonium production in strong magnetic fields have garnered significant attention in recent years, driven by the potential to uncover novel phenomena in relativistic heavy-ion collisions. A comprehensive literature review reveals that strong magnetic fields can induce a range of effects on quarkonia, including modifications to their binding energies, decay widths, and production rates. In the context of anisotropic quark-gluon plasmas, theoretical models suggest that the quarkonium production rate is sensitive to the magnetic field strength and direction. The anisotropy of the quark-gluon plasma, characterized by the momentum anisotropy parameter Xi, plays a crucial role in regulating the quarkonium production process. Several studies have employed various approaches to investigate quarkonium production in strong magnetic fields, including relativistic quantum mechanics, potential non-relativistic quantum chromodynamics, and lattice quantum chromodynamics. These approaches have yielded valuable insights into the underlying mechanisms, such as the suppression of quarkonium production due to the Landau damping effect and the enhancement of quarkonium formation via the magnetic catalysis of quark-antiquark pair creation. The literature review also highlights the importance of considering the interplay between the magnetic field and the anisotropic quark-gluon plasma in understanding quarkonium production. For instance, the anisotropy of the plasma can lead to a non-trivial dependence of the quarkonium production rate on the magnetic field strength. While significant progress has been made, the review underscores the need for further research to elucidate the complexities of quarkonium production in strong magnetic fields and anisotropic quark-gluon plasmas. Future studies should focus on refining theoretical models, incorporating additional effects such as finite temperature and density, and exploring the phenomenological implications of quarkonium production in relativistic heavy-ion collisions. The study of quark-gluon plasma, a state of matter thought to have existed in the early universe, is discussed through the use of quasiparticle models. It provides an extensive review of various models and their applications, including the chromoelectric permittivity and Debye screening in hot QCD medium, as well as the dissociation of heavy quarkonia in anisotropic hot QCD medium. The work also explores the impact of external magnetic fields on quark-gluon plasma properties, utilizing techniques such as the non-relativistic quantum mechanics framework and the Bopp's shift method. The authors delve into the thermal field theory and its implications for soft collective excitations in hot gauge theories, highlighting the importance of classical transport theory and hard thermal loops in the quark-gluon plasma. They also examine the equations of state and relativistic heavy ion collisions, emphasizing the role of quasiparticle models in understanding these phenomena. The page presents a comprehensive list of 10 key points that summarize the essence of a research paper on advanced quantum computing algorithms. 1. Quantum computing is an emerging field that leverages the principles of quantum mechanics to process information in fundamentally different ways compared to classical computers. This new paradigm offers potential solutions to complex problems that are currently intractable or require an impractically long time to solve using traditional computing methods. 2. The paper introduces a novel quantum algorithm designed to solve combinatorial optimization problems more efficiently than classical algorithms. These types of problems are common in fields such as logistics, finance, and materials science, where finding the optimal solution among a vast number of possible solutions is crucial. 3. The algorithm utilizes quantum entanglement and superposition to explore the solution space simultaneously, reducing the computational time required to find near-optimal solutions. This approach could significantly impact various industries by providing better decision-making tools and improving operational efficiency. 4. The authors also discuss the importance of quantum error correction in maintaining the coherence of quantum states during computation. They propose an innovative error correction scheme that adapts to changing environmental conditions, enhancing the reliability of quantum computations. 5. Another significant aspect of the paper is its exploration of quantum classical hybrid computing architectures. By integrating classical and quantum processors, researchers can leverage the strengths of both paradigms to tackle complex problems that would be difficult or impossible for either type of computer to solve alone. 6. The paper highlights the challenges of scaling up quantum computers while maintaining control over the quantum states. It suggests new strategies for designing scalable architectures that minimize decoherence and maximize computational fidelity. 7. In addition to these technical contributions, the paper emphasizes the need for interdisciplinary collaboration between physicists, computer scientists, and engineers to advance the field of quantum computing. This synergy is essential for overcoming the numerous technical hurdles that still hinder the development of practical quantum computers. 8. Furthermore, the authors address ethical considerations related to the potential impact of quantum computing on society. They argue that it is crucial to engage in open dialogue about the ethical implications of this technology to ensure its responsible development and deployment. 9. The paper concludes by outlining future research directions, including the development of more efficient quantum algorithms, improvements in quantum error correction techniques, and the creation of standardized benchmarks for evaluating the performance of quantum computers. 10. Overall, the paper provides a comprehensive overview of the current state of quantum computing research, highlighting both the significant progress made in recent years and the remaining challenges that must be addressed to realize the full potential of this promising technology.